You're moving at over 1,000,000 miles per hour right now, not figuratively, literally. And you have absolutely no idea. Right now, as you read this, you're spinning through space at velocities that would make a fighter jet look like it's standing still. Multiple velocities, actually, all happening at once, all stacked on top of each other, like some cosmic Russian nesting doll of motion. And the strangest part, the numbers we've been using for decades might be completely wrong. Let's start with something you can almost picture. You're sitting still right now, right? Wrong. If you're anywhere near the equator, you're spinning at roughly 1,040 miles per hour. That's faster than the speed of sound. You're already supersonic, and you haven't even gotten out of bed yet. Earth completes one full rotation every 23 hours, 56 minutes and 4 seconds, not 24 hours. That's a sidereal day, the actual time it takes for Earth to spin once relative to the distant stars. The extra 4 minutes we tack on for our 24-hour day exists because Earth is also moving around the Sun, so it needs a bit of extra rotation to bring the Sun back to the same position in the sky. Your speed changes depending on where you're standing. At 45 degrees latitude, you're moving at about 735 miles per hour. At the poles, you'd be spinning in place, moving at essentially 0 miles per hour horizontally. The calculation is simple. Take the speed at the equator and multiply it by the cosine of your latitude. But here's what makes this genuinely weird. On June 29th, 2022, Earth set a record. It completed one rotation in 1.59 milliseconds less than 24 hours. That might not sound like much, but it's the fastest day ever recorded. Earth has been speeding up. After decades of slowing down, our planet suddenly started spinning faster in 2020. Scientists think this has to do with the complex motion of Earth's molten core, the movement of our oceans and atmosphere, and possibly climate change causing ice at the poles to melt and redistribute mass toward the equator. When ice melts at the poles, mass moves toward the equator. This changes Earth's moment of inertia. It's the same principle that makes a figure skater spin faster when they pull their arms in. Earth is doing the cosmic equivalent of pulling in its arms, but that's just the first layer. The rotation is nothing compared to what comes next. Earth orbits the Sun at an average speed of 66,600 miles per hour. Not approximately. That's the actual number when you divide the circumference of Earth's orbit by the time it takes to complete one trip around the Sun. At this speed, we could cover Earth's entire diameter in 7 minutes. We could reach the Moon in 4 hours. This isn't constant velocity though. Earth's orbit is slightly elliptical, not perfectly circular. The eccentricity is about 0.017, which means our distance from the Sun varies throughout the year. Around January 3rd, we reach perihelion, our closest approach to the Sun, at about 91 million miles. At this point, we're moving at our maximum orbital speed. 6 months later, around July 4th, we hit aphelion, our farthest point at about 94 million miles, moving at our minimum speed. Kepler's laws dictate this. Planets move faster when they're closer to the Sun, and slower when they're farther away. The speed ranges from about 18.2 miles per second to 18.8 miles per second. That's a difference of about 2,100 miles per hour between our fastest and slowest points. Every single day, Earth travels approximately 1.6 million miles through space in its orbit around the Sun. By the time you finish reading this, you'll have traveled thousands of miles around the Sun without moving a muscle. Space agencies exploit this motion. When launching rockets, location matters enormously. If you launch from near the equator heading east, you get a free 1,040 mph speed boost from Earth's rotation before your engines even fire. That's why the European Space Agency launches from French Guiana. That's why NASA uses Cape Canaveral in Florida. That's why you don't see many space launch facilities in Alaska. This free velocity boost can save thousands of pounds of fuel. It can increase payload capacity. It can mean the difference between a mission succeeding or failing. Engineers must account for not just Earth's rotation, but also its orbital motion around the Sun, the target planet's orbital motion, and the precise timing of launch windows when planetary positions align favorably. But we're just getting started, because the Sun isn't sitting still either. Our entire solar system is orbiting around the center of the Milky Way galaxy at approximately 514,000 miles per hour. At this speed, an object could circle Earth's equator in less than 3 minutes. We're moving so fast that we could travel from Earth to the Moon in about 28 minutes. The center of our galaxy lies somewhere between 25,000 and 27,000 light-years away from us. Even at 500,000 miles per hour, it takes our solar system about 230 million years to complete one orbit around the galactic center. Astronomers call this a cosmic year or galactic year. Earth formed roughly 4.5 billion years ago. In all that time, our planet has only completed about 20 trips around the galaxy. 20 orbits. That's it. Dinosaurs existed during one of those orbits. They appeared during one cosmic year and vanished before it ended. The Sun's motion through the galaxy isn't a simple circle in a flat plane. There's a vertical component. Right now, the Sun sits about 50 light-years above the mid-plane of the Milky Way, moving upward at 4.3 miles per second. We oscillate above and below the galactic plane in a wave pattern, crossing through the plane approximately every 33 million years. Some scientists have speculated that these crossings might correlate with mass extinction events on Earth. When we pass through the dense galactic plane, we encounter more dust, gas, and gravitational perturbations that could disturb the Oort cloud, sending comets toward the inner solar system. The data is controversial, but the idea itself reveals something profound about how interconnected cosmic motions really are. Here's where things get genuinely strange. In November 2025, a study published in Physical Review Letters revealed something that shouldn't be possible according to our current models. Using radio galaxy observations, researchers found that our solar system might be moving through space more than 3 times faster than we thought. The previous estimate was around 515,000 miles per hour. The new study suggests the actual velocity could be significantly higher. They discovered this by analyzing the distribution of radio galaxies across the sky. Because we're moving through space, we see slightly more radio galaxies in our direction of travel, creating a subtle headwind effect in the data. This finding presents a 5 sigma deviation from expected values. In statistics, 5 sigma means the probability of this being random chance is about 1 in 3.5 million. This isn't a small discrepancy. This is a fundamental challenge to our understanding of cosmic motion. If confirmed, this could have profound implications for cosmology. It might challenge the lambda cold dark matter model that has guided our understanding of the universe for decades. But this is cutting-edge research from just months ago, so the scientific community is still investigating and attempting to confirm or refute these findings. Regardless of the exact number, we know the Milky Way itself isn't stationary. Our entire galaxy is moving through space relative to other galaxies. The Milky Way and Andromeda Galaxy are separated by about 2.5 million light-years, and they're rushing toward each other at about 250,000 miles per hour. In approximately 4.3 billion years, these two galaxies will collide. Don't panic. The collision won't be catastrophic in the way you might imagine. Galaxies are mostly empty space. The probability of actual stars colliding is incredibly small. Instead, the two galaxies will pass through each other, their gravitational interactions creating spectacular tidal forces that will dramatically alter both structures. Over the course of about 1 billion years, they'll merge into a single giant elliptical galaxy. Astronomers have already nicknamed it Milkomeda or Milkdromeda. The supermassive black holes at the centers of both galaxies, each containing millions of solar masses, will eventually spiral together and merge, sending gravitational waves rippling across the universe. Our sun and solar system will likely survive this merger. We might get flung into a different region of the combined galaxy, perhaps into the diffuse stellar halo rather than the dense galactic core where we currently reside. But Earth will probably still be orbiting the Sun, assuming our planet survives the Sun's red giant phase before the collision even happens. The local group, our collection of about 50 galaxies, including the Milky Way and Andromeda, is also moving as a unit through space. We're heading toward the Virgo cluster at approximately 185 miles per second. The Virgo cluster itself contains thousands of galaxies and sits about 65 million light-years away. But there's something even more massive pulling on us. Beyond the Virgo cluster lies a gravitational anomaly called the Great Attractor. This massive concentration of matter sits somewhere between 150 and 250 million light-years away in the direction of the constellations Centaurus and Hydra. The Milky Way, along with hundreds of thousands of other galaxies, is being pulled toward this region at hundreds of miles per second. We can't see the Great Attractor directly. It's hidden behind the zone of avoidance, a region where the dust and gas of our own galaxy obscures our view of distant space. But we can detect its gravitational influence on the motion of galaxies throughout our cosmic neighborhood. And the Great Attractor itself is part of something even larger. Recent cosmological studies have identified a supercluster of superclusters called Laniakea. The name means immense heaven in Hawaiian, which feels appropriate given its scale. Laniakea spans some 500 million light-years and contains the mass of approximately 100 quadrillion suns. Our local group, the Virgo cluster, the Great Attractor, and the Shapley supercluster, are all part of this immense cosmic structure, all flowing together toward a common gravitational center, like water draining toward the center of a massive basin. Understanding these large-scale motions helps cosmologists map the distribution of matter in the universe and test theories about dark matter and dark energy, which brings us to perhaps the most mind-bending measurement of all. The cosmic microwave background radiation provides what might be the closest thing we have to an absolute reference frame for measuring motion through the universe. This radiation represents the oldest light in the universe, released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely through space. The Milky Way is moving at approximately 1.3 million miles per hour relative to the cosmic microwave background frame. This motion creates a slight temperature variation in the background radiation, called the dipole anisotropy. The radiation appears slightly warmer in the direction we're moving and slightly cooler in the opposite direction. By measuring this temperature difference with incredible precision, astronomers can determine our motion relative to what is essentially the universe's rest frame. The CMB appears warmer by about 1 part in 1,000 in the direction of our motion. Modern instruments can measure these tiny temperature variations to an accuracy of millionths of a degree. This is where things become almost philosophical. What does it mean to measure our speed relative to radiation that fills all of space? What does it mean to be moving at 1.3 million miles per hour relative to the universe itself? And with all these velocities stacked on top of each other, spinning, orbiting, circling, rushing through space in multiple directions simultaneously, why don't we feel any of it? The answer lies in a principle so fundamental to physics that we take it for granted every moment of our lives. You can't feel constant motion, only acceleration. Right now, you're sitting still relative to everything around you. Your coffee mug isn't sliding across the table. The air in the room isn't blasting past your face at 1,000 miles per hour. Everything in your immediate environment is moving with you, spinning with Earth, orbiting with Earth, racing through the galaxy with Earth. There's no relative motion between you and your surroundings, so there's nothing to feel. Galileo figured this out in the 1600s. He described what we now call Galilean relativity, using the example of a ship sailing smoothly across calm water. If you're below deck in a windowless cabin, you can't tell whether the ship is moving or sitting still in the harbour. Toss a ball in the air, and it falls straight back down into your hand. Pour water, and it falls straight down into your cup. Everything behaves exactly as it would on solid ground. Einstein later refined this into his principle of relativity, which states that the laws of physics are the same in all inertial reference frames. An inertial reference frame is just a fancy way of saying moving at constant velocity in a straight line. As long as you're not accelerating, you can't detect your own motion without looking outside your reference frame. Earth's rotation is essentially constant. Yes, the planet is spinning at over 1,000 miles per hour at the equator, but that speed doesn't change from moment to moment. You're not speeding up or slowing down. You're just moving, and everything around you is moving right along with you. The same principle applies to Earth's orbit around the Sun. We're hurtling through space at 67,000 miles per hour, but that velocity is nearly constant. The orbit is slightly elliptical, which means there are tiny variations in speed throughout the year, but these changes are so gradual that we can't perceive them. Here's what makes this even more interesting. You do actually feel one effect of Earth's rotation, but it's so subtle you've never noticed it. The centrifugal force from Earth's spin creates a slight outward push that counteracts gravity by about 0.3% at the equator. This makes you weigh slightly less at the equator than you would at the poles. If you weigh 150 pounds at the North Pole, you'd weigh about 149.5 pounds at the equator, half a pound lighter just from the spin. But the change is gradual enough that you'd never notice it in your daily life. Earth's gravity holds us firmly in place despite all this motion. At the equator, where the centrifugal effect is strongest, gravity still pulls with more than 99% of its full force. To actually fling objects off the surface, Earth would need to spin about 17 times faster than it currently does. At that speed, a day would last about 84 minutes instead of 24 hours. But there's something else that keeps all these motions from affecting us. The atmosphere moves with the planet. This is crucial. If Earth's surface was spinning beneath a stationary atmosphere, we'd experience constant winds of over 1,000 miles per hour at the equator. Hurricanes would seem like gentle breezes by comparison. Instead, the atmosphere is dragged along by friction with the surface and by Earth's gravity. The air molecules are moving right along with us, spinning at the same rate as the ground beneath our feet. This is why you can throw a ball straight up and have it land back in your hand. The ball, the air, and you are all moving together. The same principle extends to all our cosmic motions. As Earth orbits the Sun, it carries its atmosphere along. As the solar system orbits the galaxy, it carries all its planets and their atmospheres. Everything moves together as a unit. There's one exception to this smooth motion though, one place where you actually can feel Earth's rotation, at least indirectly. The Coriolis effect. Because Earth is rotating, objects moving across its surface experience an apparent deflection. In the northern hemisphere, moving objects curve to the right. In the southern hemisphere, they curve to the left. This isn't because any force is pushing them sideways. It's because the ground beneath them is rotating. The Coriolis effect is too weak to notice in everyday life. That myth about toilets flushing in different directions in different hemispheres. Complete nonsense. The effect is far too small to influence something as chaotic as water swirling down a drain. But on larger scales, the Coriolis effect becomes significant. It's what causes hurricanes to rotate. It influences ocean currents. It affects the flight paths of long-range artillery shells and intercontinental missiles. Weather systems, wind patterns, the circulation of the oceans, all shaped by the fact that we're standing on a rotating sphere. And here's something that might surprise you. Earth's rotation is actually slowing down. Gradually, imperceptibly, but measurably. The planet spins slightly slower today than it did when the dinosaurs walked the Earth. The Moon is responsible. Its gravitational pull creates tidal bulges in Earth's oceans. As these bulges sweep around the planet, they create friction with the ocean floor and coastlines. This friction dissipates energy, and that energy has to come from somewhere. It comes from Earth's rotational energy. The planet is slowing down by about 1.7 milliseconds per century. That doesn't sound like much, but over geological timescales, it adds up. 4 billion years ago, when Earth was young, a day lasted only about 6 hours. The planet was spinning much faster, and the Moon was much closer. As Earth slows down, the Moon gradually drifts farther away. It's currently receding at about 1.5 inches per year. The same tidal forces that slow Earth's rotation transfer angular momentum to the Moon, pushing it into a slightly higher orbit. But there's a twist to this story. Recent measurements show that Earth's rotation has actually been speeding up slightly over the past few years. On June 29th, 2022, Earth completed a full rotation 1.59 milliseconds faster than the standard 86,400 seconds we use to define a day. This is the opposite of the long-term trend. Scientists aren't entirely sure what's causing it. The leading theories point to changes in Earth's molten core, shifts in ocean currents and atmospheric circulation, and possibly the redistribution of mass as ice at the poles melts due to climate change. When polar ice melts, water flows toward the equator. This redistributes mass from near Earth's axis of rotation toward the edge. You might think this would slow the rotation, like a spinning figure skater extending their arms. But the situation is more complex because of how this mass redistribution interacts with Earth's slightly oblate shape and the gravitational effects of the Sun and Moon. These variations in rotation speed are tiny, but they matter. Our modern timekeeping is based on atomic clocks that tick with extraordinary precision. A day is defined as exactly 86,400 seconds. But Earth doesn't care about our definitions. It rotates at whatever rate physics dictates. When Earth's rotation drifts too far from our atomic time standard, we add or subtract leap seconds to keep them synchronized. Since 1972, we've added 27 leap seconds to compensate for Earth's gradual slowdown. But if Earth continues its recent trend of speeding up, we might need to introduce the first ever negative leap second, actually removing a second from our clocks to keep them aligned with Earth's rotation. This might seem like an obscure technical detail, but it has real implications. Computer systems around the world are synchronized to atomic time. GPS satellites depend on precise timing. Financial markets use timestamps accurate to milliseconds. A sudden 1-second adjustment can cause glitches in systems that weren't designed to handle time moving backward. Now let's consider the practical applications of understanding all these motions. Space agencies have learned to use Earth's rotation to their advantage. When launching rockets, every bit of velocity helps. A rocket launched eastward from the equator already has a head start of about 1,000 miles per hour before its engines even fire. This is why space agencies prefer launch sites near the equator. The European Space Agency launches from French Guiana, just 5 degrees north of the equator. The United States uses Cape Canaveral in Florida at 28 degrees north latitude. Russia's Baikonur Cosmodrome in Kazakhstan sits at 46 degrees north, which is less ideal, but was chosen for other strategic reasons during the Cold War. The difference in launch efficiency is substantial. A rocket launched from the equator gets the full benefit of Earth's rotational speed. Launch from higher latitudes and you get less of a boost. At the poles, you get no benefit at all from the rotation. This free velocity boost can save enormous amounts of fuel. Rocket fuel is expensive and heavy. Every kilogram of fuel you don't need to carry is a kilogram you can use for payload or additional equipment. For missions to the International Space Station or satellites destined for equatorial orbits, launching eastward from near the equator is the most efficient option. But Earth's rotation isn't the only motion that matters for space travel. Engineers also have to account for Earth's orbital motion around the Sun. When planning missions to other planets, they wait for launch windows when Earth and the target planet are favorably aligned. These alignments follow predictable patterns based on the orbital periods of the planets involved. Mars missions, for example, have optimal launch windows roughly every 26 months when Earth and Mars are positioned to allow the most efficient trajectory. Spacecraft also use gravitational assists, sometimes called slingshot maneuvers, to gain speed without burning fuel. A spacecraft can fly close to a planet, using the planet's gravity to alter its trajectory and velocity. The planet's orbital motion gets transferred to the spacecraft, accelerating it toward its destination. The Voyager probes used a series of these gravitational assists to visit Jupiter, Saturn, Uranus, and Neptune. Without these assists, the missions would have required far more fuel or taken decades longer to complete. All of this requires precise knowledge of planetary motions, not just where the planets are now, but where they'll be months or years in the future when the spacecraft arrives. Engineers calculate trajectories that account for Earth's rotation, its orbit around the Sun, the target planet's orbit, and sometimes the orbits of multiple planets if the mission involves several gravitational assists. These calculations are possible because planetary motions are predictable. Newton's laws of motion and gravity, refined by Einstein's general relativity, allow us to predict where planets will be with extraordinary accuracy. We can calculate planetary positions centuries into the future or reconstruct where they were thousands of years in the past. Ancient astronomers used eclipse records to study subtle changes in Earth's rotation. A solar eclipse visible from a particular location on Earth occurs because the Moon passes directly between that location and the Sun. By comparing ancient eclipse records with calculations of where eclipses should have occurred based on current orbital motions, astronomers can detect how Earth's rotation has changed over millennia. Babylonian clay tablets describe eclipses from over 2,500 years ago. Chinese astronomical records go back even further. These ancient observations provide data points that reveal Earth's gradual slowdown over historical time. The principle that allows us to not feel all this motion, the principle that constant velocity is undetectable without an external reference, is the same principle that makes modern physics work. Einstein built his theory of special relativity on this foundation. The speed of light is constant in all reference frames precisely because there's no absolute reference frame against which to measure motion. This might seem abstract, but it has concrete implications. GPS satellites orbit Earth at about 14,000 kilometers per hour. They're moving at a different velocity than you are on the ground, and they're in a weaker gravitational field. Both special relativity and general relativity predict that time will pass at a slightly different rate for the satellites than for you. If GPS didn't account for these relativistic effects, the system would accumulate positioning errors of several kilometers per day. The fact that your phone can pinpoint your location to within a few meters is direct proof that relativity is real and that all these different motions create measurable effects on the passage of time itself. The connection between motion and time doesn't stop at GPS satellites. Every moving object in the universe experiences time differently based on its velocity and gravitational environment. A clock on Mount Everest runs faster than one at sea level because it's farther from Earth's center and in a slightly weaker gravitational field. The difference is tiny, about 30 nanoseconds per day, but atomic clocks are precise enough to measure it. This gets more dramatic when we zoom out to cosmic scales. Our entire solar system is moving through the Milky Way galaxy at roughly 230 kilometers per second. That's over 800,000 kilometers per hour, fast enough to circle Earth's equator in less than 3 minutes. But here's where it gets weird. A recent study published in November 2025 suggests we might be moving even faster than that. The research team analyzed the distribution of radio galaxies across the sky and found something unexpected. Because the solar system is moving through space, we see slightly more radio galaxies in our direction of travel, like bugs hitting a windshield create a pattern. This cosmic headwind revealed a velocity more than 3 times greater than previous calculations suggested. The study shows a 5 sigma deviation from expected values. In statistics, 5 sigma means the result has less than a 1 in 3.5 million chance of being random noise. That's the same confidence level physicists used when they announced the discovery of the Higgs boson. If this finding holds up under scrutiny, it could challenge fundamental assumptions about cosmology. The lambda cold dark matter model, our current best explanation for how the universe works, might need serious revision. But this is cutting-edge research. Other scientists need to verify it independently before we rewrite textbooks. What we know for certain is that the Milky Way itself is moving through space. Our galaxy and the Andromeda Galaxy are hurtling toward each other at about 123 kilometers per second. That's 250,000 miles per hour. They're separated by roughly 2.5 million light years, and they're on a collision course. Don't cancel your long-term plans, though. The collision won't happen for another 4 billion years. When it does, it won't be like 2 cars crashing. Galaxies are mostly empty space. The stars are so far apart that actual stellar collisions will be extremely rare. Instead, the 2 galaxies will pass through each other, their gravitational fields distorting both structures. Then they'll swing back around and merge over the course of about 1 billion years. The result will be a single giant elliptical galaxy. Astronomers have already nicknamed it Milkomeda or Milkdromeda. Our Sun will probably survive the merger, though it might end up in a completely different part of the combined galaxy. Perhaps in the diffuse stellar halo rather than where it is now. But the Milky Way and Andromeda aren't moving in isolation. They're part of the local group, about 50 galaxies bound together by gravity, and the local group itself is moving as a unit, pulled by even larger gravitational structures, about 150 to 250 million light-years away. In the direction of the constellations Centaurus and Hydra sits something called the Great Attractor. It's a massive concentration of matter, equivalent to tens of thousands of galaxies. Its gravitational pull affects our motion and the motion of hundreds of thousands of other galaxies. Actually, the Great Attractor is just part of an even larger structure. Recent mapping of cosmic flows revealed something called Laniakea, a supercluster of superclusters. The name means immense heaven in Hawaiian, which fits because Laniakea spans 500 million light-years and contains the mass of roughly 100 quadrillion suns. Everything we've discussed so far, the local group, the Virgo cluster, the Great Attractor, the Shapley supercluster behind it, all of these are part of Laniakea, all flowing together toward a common gravitational center like water draining toward a basin. This creates layers of motion stacked on top of each other. Earth spins on its axis. Earth orbits the Sun. The Sun orbits the galactic center. The Milky Way moves through the local group. The local group falls toward the Virgo cluster. The Virgo cluster flows toward the Great Attractor. Everything moves within Laniakea, and Laniakea itself moves relative to other superclusters. So how do we measure all this motion? What's our reference point? Astronomers use the cosmic microwave background, radiation. It's the afterglow of the Big Bang, released about 380,000 years after the universe began, when it cooled enough for atoms to form and photons to travel freely. This ancient light fills all of space, coming from every direction. The CMB is remarkably uniform, the same temperature everywhere to within 1 part in 25,000. But our motion through space creates a subtle pattern. The radiation appears slightly warmer in the direction we're moving and slightly cooler in the opposite direction. This is the Doppler effect applied to the entire observable universe. By measuring this temperature difference, astronomers determined that the Milky Way is moving at about 552 kilometers per second relative to the CMB. That's over 1.2 million miles per hour. The direction is toward a point in the constellation Hydra. This CMB motion represents our velocity relative to the closest thing we have to an absolute reference frame. The CMB reflects the large-scale average motion of matter in the universe. It's the cosmic rest frame, though Einstein would remind us that even this is technically just another relative measurement. The local group's motion can be broken down into components. Part of it comes from the Milky Way's own peculiar velocity, its motion relative to nearby galaxies. Part comes from the local group, falling toward the Virgo cluster at roughly 300 kilometers per second. Part comes from larger scale flows toward the Great Attractor and beyond. All these velocities add up vectorially. You can't just sum the numbers because motion in different directions needs to be combined using geometry. The math involves three-dimensional vectors and coordinate transformations. When astronomers account for all the components, they can determine our total motion relative to the CMB with remarkable precision, down to the exact direction and speed. This precision comes from analyzing the temperature variations across the entire sky. Modern satellites measure the CMB temperature to within millionths of a degree. They create detailed maps showing not just the dipole anisotropy from our motion, but also tiny fluctuations that represent the seeds of cosmic structure from the early universe. Those tiny fluctuations, variations of about 1 part in 100,000, eventually grew under gravity to become galaxies and galaxy clusters. Regions that were slightly denser than average pulled in more matter. Over billions of years, this created the cosmic web we see today, with galaxies arranged in filaments and sheets surrounding vast empty voids. The pattern of these fluctuations tells us about conditions in the universe when it was less than 400,000 years old. By studying them, cosmologists have measured fundamental parameters like the age of the universe, 13.8 billion years, its composition, about 5% ordinary matter, 27% dark matter, 68% dark energy, and its geometry, flat, meaning parallel lines stay parallel forever. This is possible because the CMB acts like a fossil record. It preserves information from a time before stars, before galaxies, before most of cosmic history. The photons that make up the CMB have been traveling through space for over 13 billion years, and they carry with them a snapshot of the infant universe. When you think about measuring motion through space, you need something to measure against. On Earth, we measure speed relative to the ground. In space, we measure orbital velocities relative to the central body. But for cosmic velocities, the motion of galaxies and galaxy clusters, the CMB provides the ultimate reference point. Astronomers determine velocities by analyzing light. When an object moves toward us, its light gets compressed to shorter, bluer wavelengths. When it moves away, the light stretches to longer, redder wavelengths. This Doppler shift works for sound waves too. It's why an ambulance siren drops in pitch as it passes you. For nearby stars and galaxies, measuring the Doppler shift reveals their motion with incredible precision. Modern instruments can detect velocity changes as small as a few meters per second. This is how we discover exoplanets, by measuring the tiny wobble they create in their parent star's motion. For distant galaxies, the measurement gets more complicated. The redshift includes both their peculiar velocity and the cosmological redshift from the expansion of space itself. At great distances, the expansion dominates. Galaxies billions of light-years away appear to be receding at tremendous speeds, not because they're moving through space, but because the space between us and them is stretching. This raises a fascinating question about the nature of velocity itself. When we say a distant galaxy is receding at a certain speed, what does that mean? It's not moving through space in the conventional sense. Space itself is expanding, carrying the galaxy along with it. At the larger scales, the concept of motion becomes ambiguous, blending into the expansion of space-time. Einstein's general relativity describes this expansion mathematically. The universe doesn't have an edge or a center. Every point is expanding away from every other point, like dots on an inflating balloon. An observer in any galaxy would see all other galaxies receding, with more distant ones receding faster. This expansion creates cosmic horizons. There are regions of the universe so far away that their light will never reach us, because the space between us is expanding faster than light can cross it. Not because anything is moving faster than light through space, but because space itself is expanding too rapidly. The speed of light remains the universal speed limit for motion through space. But space itself isn't constrained by that limit. During cosmic inflation, a brief period shortly after the Big Bang, space expanded exponentially, far faster than light speed. This didn't violate relativity because it wasn't matter or energy moving, just the fabric of space-time stretching. Understanding all these motions requires tracking multiple reference frames simultaneously. Earth's rotation relative to the stars, Earth's orbit relative to the Sun, the Sun's orbit relative to the galactic center, the galaxy's motion relative to the local group, the local group's motion relative to the CMB. Each frame has its own velocity, and converting between them requires careful calculation. This is why space agencies plan missions years in advance. To send a probe to Jupiter, engineers must account for Earth's rotation, Earth's orbital motion, Jupiter's orbital motion, and the changing geometry as both planets move. The spacecraft follows a curved path through space, not a straight line, because everything is moving. The Voyager probes, launched in 1977, used gravitational assists from multiple planets. They flew close to Jupiter, using its gravity and orbital motion to gain speed and redirect towards Saturn. Then Saturn's gravity sent them toward Uranus and Neptune. Each encounter was timed precisely, accounting for planetary positions years in the future. Those calculations required knowing exactly where the planets would be, which means knowing their orbital velocities to high precision. A small error compounds over time. If your initial trajectory is off by even a fraction of a degree, months later you might miss your target by millions of kilometers. All of this motion, from Earth's spin to the expansion of the universe, happens without us feeling a thing. We're along for the ride, moving at hundreds of thousands of kilometers per hour through space, and our coffee sits perfectly still on the table. That perfect stillness is an illusion, but it's one that reveals something fundamental about how motion actually works. Your brain interprets motion through change. When you're in a car accelerating from a stoplight, you feel pressed back into your seat. When the driver hits the brakes, you lurch forward. But cruising down the highway at a steady 100 kilometers per hour, nothing. The sensation vanishes completely. Earth's rotation creates no acceleration you can detect. Neither does its orbit around the sun. The solar system's journey through the galaxy. Imperceptible. These motions are so smooth, so constant, that from your perspective, they might as well not exist at all. This principle goes deeper than comfort. It's foundational to physics itself. Galileo figured this out in the 1600s while watching ships in harbor. A sailor below deck couldn't tell whether the ship was docked or moving steadily through calm water. Drop a ball, and it falls straight down either way. Toss it up, and catch it with the same ease. The motion of the ship doesn't interfere because everything inside shares that motion equally. Einstein later formalized this insight as the principle of relativity. There's no experiment you can perform inside a closed system that reveals uniform motion. You need an external reference point. Without looking outside, the sailor can't distinguish between a stationary ship and one moving at constant velocity. This is why you don't feel Earth's spin. You're not stationary while the ground races beneath you. You're moving with it. The atmosphere moves with it. The coffee in your cup moves with it. Everything participates in the same motion, so relative to each other, nothing moves at all. But here's where it gets interesting. While you can't feel constant velocity, you absolutely can feel acceleration. Change in motion reveals itself immediately. When Earth rotates, it's actually accelerating you constantly toward its center. This centripetal acceleration keeps you moving in a circle instead of flying off in a straight line. So why don't you notice? The acceleration is tiny. At the equator, where it's strongest, centripetal acceleration counteracts Earth's gravity by only 0.3%. You weigh slightly less there than you would at the poles, but the difference is imperceptible. Your bathroom scale might show it, but your body can't. To actually feel Earth's rotation, it would need to spin much faster. Calculations show the equator would need to reach about 28,000 kilometers per hour, 17 times its current speed, before the centrifugal effect overcame gravity. At that speed, objects at the equator would become weightless and float away. Earth's spin is nowhere near that extreme. But there are consequences we can measure. The planet bulges slightly at the equator because of centrifugal force. The difference between Earth's equatorial and polar diameters is about 43 kilometers. Not much compared to Earth's total diameter of 12,700 kilometers, but enough to matter for satellite orbits and GPS calculations. That bulge also affects gravity. Stand at the equator and you're farther from Earth's center than someone at the poles. Greater distance means slightly weaker gravitational pull. Combined with the centrifugal effect, you weigh about 0.5% less at the equator than at the poles. These variations seem trivial until you're launching rockets or positioning satellites. Then they become critical. GPS satellites orbit at precisely calculated altitudes. Their clocks run slightly faster than clocks on Earth's surface because they experience weaker gravity, a prediction of Einstein's general relativity. The difference is only microseconds per day, but GPS requires nanosecond precision. Without correcting for both gravitational and velocity-related time dilation, GPS would accumulate errors of several kilometers per day. The International Space Station orbits at about 400 kilometers altitude, traveling at 7.66 kilometers per second. Astronauts aboard experience microgravity not because there's no gravity up there. Earth's gravitational pull at that altitude is still about 90% of surface strength, but because they're in constant free fall. The station and everything inside it falls toward Earth at the same rate, creating the sensation of weightlessness. From the astronaut's perspective, they're floating in place. From ours on the ground, they're screaming around the planet at 27,600 kilometers per hour, completing an orbit every 90 minutes. Both perspectives are valid. That's relativity. Now scale up from Earth's rotation to its orbit around the Sun. You're traveling at 107,000 kilometers per hour right now as Earth circles the Sun. But again, you feel nothing. The orbit is smooth enough that acceleration toward the Sun goes unnoticed. Your inner ear can't detect it. Your coffee doesn't slosh. But this motion has observable effects. Earth's orbit isn't perfectly circular. It's slightly elliptical, with the Sun at one focus. Early January brings us closest to the Sun, about 147 million kilometers, while early July takes us farthest at 152 million kilometers. That 5 million kilometer difference affects Earth's orbital speed. Kepler's laws of planetary motion dictate that planets move faster when closer to the Sun. Earth reaches maximum orbital speed of about 30.29 kilometers per second at perihelion in January. 6 months later, at aphelion, it slows to about 29.29 kilometers per second. You're traveling 1 kilometer per second faster in January than in July. That's 3,600 kilometers per hour difference in speed, depending on the time of year. Still feel nothing? Of course not. The change happens gradually over 6 months. Acceleration is spread out so smoothly that it's imperceptible, but look at the stars carefully over months, and you'll notice parallax. Nearby stars appear to shift position slightly against the background of more distant stars, as Earth moves from one side of its orbit to the other. This parallax provides a direct measurement method for stellar distances. The nearest star system, Alpha Centauri, shows parallax of about 0.75 arcseconds. That's the angular width of a dime viewed from 4 kilometers away. Tiny, but measurable with good telescopes. And it proves Earth is moving. Ancient astronomers couldn't detect stellar parallax, which is why they reasonably concluded Earth must be stationary. If Earth orbited the Sun, nearby stars should show parallax. The absence of detectable parallax suggested either Earth didn't move, or the stars were incomprehensibly far away. Turns out they're incomprehensibly far away. Detecting stellar parallax required telescopes precise enough to measure fractions of an arcsecond. Friedrich Bessel finally succeeded in 1838, measuring the parallax of 61 Cygni. That single measurement confirmed Earth's motion around the Sun and revealed the true scale of interstellar distances. Now, consider the Sun's orbit around the galaxy. Our solar system circles the Milky Way's center at about 230 kilometers per second. That's over 800,000 kilometers per hour. At this speed, you could travel Earth's circumference in less than 3 minutes. Yet you feel nothing. The motion is constant. The acceleration toward the galactic center is imperceptible. Your coffee remains calm. But this motion shapes everything about our cosmic neighborhood. The sun doesn't orbit alone. It drags its entire planetary system along. All the planets, asteroids, comets, everything gravitationally bound to the sun, makes this journey together. We're all passengers on a stellar carousel that takes 230 million years to complete one rotation. That duration is sometimes called a cosmic year. Earth has existed for about 4.5 billion years, meaning our planet has completed roughly 20 trips around the galaxy. Dinosaurs roamed Earth during the previous galactic orbit. The one before that predates complex life entirely. The Sun's galactic orbit isn't a simple circle either. It follows a slightly elliptical path, and it also oscillates up and down through the galactic plane like a wave. Right now, we're about 50 light years above the midplane, moving upward at 7 kilometers per second. In about 14 million years, we'll reach maximum height, then descend back through the plane. This vertical oscillation means the Sun crosses the galactic midplane roughly every 33 million years. Some researchers have speculated this might correlate with mass extinction events on Earth, though the evidence remains controversial. The idea is that passing through the denser galactic plane could disturb the Oort cloud, a spherical shell of comets surrounding the solar system, sending comets careening into the inner solar system and increasing impact risks. Whether that's true or not, the point stands. The Sun's galactic motion isn't just horizontal. It's three-dimensional, complex, influenced by the gravitational pull of the galaxy's spiral arms and dark matter halo. Speaking of which, here's something wild. When astronomers measure how fast stars orbit in spiral galaxies, the speeds don't match predictions based on visible matter. Stars in the outer regions of galaxies orbit far too quickly. Based on the gravity of stars and gas we can see, those outer stars should be moving slower, or they should fly off into intergalactic space entirely. They don't, which means something invisible is providing extra gravitational pull. That something is dark matter. Galaxies are embedded in massive halos of this mysterious substance that outweighs all the visible stars and gas combined. Dark matter doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation at all. We detect it only through gravity. The Milky Way's dark matter halo extends far beyond the visible disk of stars. Current estimates suggest it reaches out at least 600,000 light-years from the galactic center, 10 times farther than the visible edge of the galaxy. This halo contains several times more mass than all the stars in the Milky Way combined. You're inside this dark matter halo right now. Dark matter particles are probably passing through your body constantly, but they interact so weakly with ordinary matter that they pass straight through without leaving any trace. Scientists have built sensitive detectors deep underground, shielded from cosmic rays and background radiation, hoping to catch a dark matter particle interacting with ordinary atoms. So far, despite decades of searching, no confirmed detections. The hunt continues. Understanding dark matter is crucial for understanding galactic motion. The Sun's orbital speed of 230 kilometers per second. That's determined largely by the dark matter halo's gravitational pull, not just by visible stars. Without dark matter, galactic rotation curves make no sense, and galaxies themselves are moving. The Milky Way isn't stationary in space. It's part of the Local Group, a collection of about 50 galaxies bound together by gravity. The Local Group is dominated by two large spiral galaxies, our Milky Way and the Andromeda Galaxy. Andromeda is approaching us at about 110 kilometers per second. In roughly 4 billion years, these two galaxies will collide. Don't worry about that. The word collision is misleading. Galaxies are mostly empty space. When they merge, very few stars will actually hit each other. Instead, the two galaxies will pass through each other, their gravity distorting spiral arms and triggering intense bursts of star formation as gas clouds collide and compress. Over about 1 billion years, the two galaxies will merge completely, forming a single elliptical galaxy. Astronomers have already nicknamed it Milkomeda. The Sun will likely survive this merger. It'll probably end up in a different region of the combined galaxy, possibly in the diffuse stellar halo rather than the dense core. But 4 billion years is a long time. The Sun will be nearing the end of its life by then anyway. Here's what's remarkable. Despite Andromeda approaching at 110 kilometers per second, and despite the Milky Way itself moving, you still feel nothing. All these galactic motions are smooth and constant from your perspective. But zoom out further and things get even stranger. The Local Group, containing our Milky Way and Andromeda, along with about 50 smaller galaxies, doesn't just sit still in space. It's moving as a unit, and this is where things get seriously weird. The Local Group is falling towards something massive, something so enormous it's pulling hundreds of thousands of galaxies across hundreds of millions of light years of space. It's called the Great Attractor, and we discovered it by accident. In the 1970s, astronomers mapping galaxy velocities noticed something odd. Galaxies in our region of the universe weren't moving randomly. They showed a coherent flow pattern, a drift toward one specific direction in space, toward the constellation Hydra Centaurus. Something out there was pulling. The Great Attractor is located about 150 to 250 million light years away. It's not a single object. It's a massive concentration of matter. Galaxy clusters, superclusters, dark matter, creating a gravitational well so deep it influences galactic motion across vast distances. The Milky Way is being pulled toward it at about 600 kilometers per second. That's our velocity through space, relative to the cosmic microwave background. The CMB is the afterglow of the Big Bang, radiation from when the universe was only 380,000 years old. It fills all of space uniformly, almost uniformly. When satellites measure the CMB's temperature across the sky, they detect a dipole pattern. One direction appears slightly warmer, the opposite direction appears slightly cooler. This isn't because the CMB itself varies. It's the Doppler effect from our motion through space. Moving toward radiation compresses its wavelengths, making it appear warmer. Moving away stretches wavelengths, making it appear cooler. By measuring this temperature difference, astronomers can determine our absolute velocity through the universe, or at least the closest thing to absolute velocity that exists. The result? The Milky Way moves at 552 kilometers per second relative to the CMB frame. That's over 1.2 million miles per hour, and the Local Group as a whole is moving at roughly 600 kilometers per second toward a point between the constellations Leo and Crater. But even the Great Attractor isn't the whole story, because it's being pulled too. In 2014, astronomers published a paper that redrew the cosmic map. They'd been studying galaxy velocities across a huge volume of space, and they discovered that the Great Attractor, the Virgo cluster, our local group, and thousands of other galaxy groups are all part of a single superstructure, a supercluster of superclusters. They named it Laniakea, Hawaiian for immense heaven, and immense doesn't begin to cover it. Laniakea spans 500 million light years. It contains approximately 100,000 large galaxies. The total mass? About 100 quadrillion times the mass of the Sun. Our entire local group, with its 50 galaxies, is a tiny speck on the outer edge of this structure. All the galaxies in Laniakea are flowing together like rivers draining toward a basin. The basin is the gravitational center of the supercluster, and we're all falling into it at hundreds of kilometers per second. This completely changed how astronomers think about cosmic structure. Galaxies aren't randomly scattered through space. They're organized into clusters, which are organized into superclusters, which are organized into even larger filaments and sheets separated by vast cosmic voids. The universe has a web-like structure on the largest scales. You're riding one strand of that cosmic web right now. Earth orbits the Sun. The Sun orbits the galactic center. The galaxy falls toward the Great Attractor. The Great Attractor flows with Laniakea, and Laniakea itself is moving through space. The speed stack. They don't simply add. Relativistic effects prevent that. But the motions compound. Your velocity through space depends entirely on your reference frame. Relative to Earth's surface, you're nearly stationary. Relative to the Sun, you're moving at 30 kilometers per second. Relative to the galactic center, 230 kilometers per second. Relative to the CMB, over 550 kilometers per second. None of these answers is more correct than the others. Motion is relative. Always. Einstein taught us that. There's no absolute rest frame in the universe. No cosmic signpost marking, here is stationary, everything else is moving. The CMB comes close to providing a universal reference frame, but even that's just measuring motion relative to the average distribution of matter in the early universe. This raises a philosophical question. If all motion is relative, what does it mean to ask how fast Earth is moving? Moving compared to what? The question needs a reference point to have meaning. Physicists sometimes talk about peculiar velocity. That's an object's motion relative to the Hubble flow, the expansion of the universe itself. Galaxies recede from each other as space expands, but they also have their own individual motions on top of that expansion. Those individual motions are peculiar velocities. The Milky Way's peculiar velocity is about 600 kilometers per second. That's its motion through space after you account for cosmic expansion. It's the velocity caused by local gravitational effects, the pull of the Great Attractor, the flow toward Laniakea's center, and smaller-scale gravitational interactions with nearby galaxy groups. But here's something that'll mess with your head. While we're falling toward the Great Attractor, and while Andromeda is approaching us, and while all these gravitational interactions are happening, the universe itself is expanding. Space is stretching. Distant galaxies are receding from us faster than light, not moving through space faster than light. That's impossible. But space itself is expanding so rapidly that the distance between us and those galaxies increases faster than light could travel across it. This doesn't violate relativity because nothing is moving through space faster than light. The space between objects is increasing. The expansion of the universe is accelerating. Dark energy, whatever that is pushing space apart at an increasing rate. This creates a cosmic horizon. Beyond a certain distance, galaxies are receding so fast that light from them will never reach us. They're beyond our observable universe, not because they're too far away, but because the expansion of space prevents their light from ever making the journey. Within our local region, gravity wins over expansion. The Milky Way and Andromeda are gravitationally bound. Expansion won't prevent their collision. The local group is held together by gravity. Even Laniakea, that immense structure spanning 500 million light-years, is bound by gravity. But beyond Laniakea, other superclusters are receding. The expansion of space dominates. Eventually, in hundreds of billions of years, every galaxy outside our local group will have receded beyond the cosmic horizon. Future astronomers in that distant era will observe a universe that appears to contain only their own galaxy. They'll have no way to discover cosmic expansion, no way to learn about the Big Bang. The evidence will have literally disappeared over the horizon. We live in a special time. A time when the universe is old enough for complex structures to form, but young enough that we can still observe cosmic history. A few 100 billion years from now, that window will have closed, but that's the far future. Right now, you're moving through space at over 500,000 kilometers per second, relative to the CMB. You're orbiting the galactic center at 230 kilometers per second. You're racing around the sun at 30 kilometers per second. You're spinning with Earth's rotation at up to 1,674 kilometers per hour. Stack all those motions together, not by simple addition, because relativity prevents that, but through proper relativistic velocity combination, and you get your total velocity through space, which is meaningless without specifying relative to what. The November 2025 study suggesting our solar system moves 3 times faster than previously calculated. That's based on radio galaxy observations. Scientists analyzed the distribution of radio galaxies across the sky and noticed an asymmetry. Slightly more radio galaxies appear in our direction of motion through space, like a headwind creating resistance. This technique is independent of previous methods. It doesn't rely on measuring Doppler shifts or gravitational effects. It's purely statistical, based on galaxy distribution patterns. And it suggests our velocity relative to the galactic center might be significantly higher than the accepted 230 kilometers per second. The study presents a 5 sigma deviation. In statistics, that's extremely significant. It means the probability of this result occurring by random chance is less than 1 in a million. If confirmed, this would require revising our models of galactic dynamics and potentially our understanding of dark matter distribution. But it's very recent. Other astronomers need to verify the findings. Alternative explanations need to be ruled out. Maybe the radio galaxy distribution is affected by something else, selection effects in how we detect them, cosmic structure along our line of sight, or systematic errors in the observations. Science works through confirmation and replication. One study, no matter how statistically significant, doesn't overturn decades of measurements. But it's exactly the kind of anomaly that leads to breakthroughs. Sometimes the data that doesn't fit is telling you something profound. Imagine if the solar system really is moving 3 times faster than we thought. That would imply either more mass in the galaxy than current models predict, or a different distribution of dark matter, or possibly modifications to how gravity works on galactic scales. Any of those would be revolutionary. This is how progress happens in astronomy. Someone notices something doesn't quite fit. They dig deeper. Sometimes it's a measurement error. Sometimes it's a new discovery that changes everything. The point is, even after decades of studying galactic motion, we're still refining our measurements, still discovering new details about how fast we're moving and what's causing that motion. The universe keeps surprising us. You're on a planet spinning at over 1,000 miles per hour, orbiting a star at 67,000 miles per hour. That star is orbiting a galaxy at over 500,000 miles per hour. The galaxy is falling through space at over 1,000,000 miles per hour, and all of it is happening in a universe that's expanding faster than light at the largest scales. Yet none of this motion is random. None of it is chaotic. Every velocity we've discussed follows precise mathematical laws that have held for billions of years. Earth's rotation isn't slowing randomly. It's being systematically decelerated by tidal friction with the Moon. That same friction is pushing the Moon away from Earth by about 3.8 centimeters per year. Measure the Moon's distance, calculate backward, and you discover that 4.5 billion years ago, the Moon was so close that days were only 5 hours long. The tides were monstrous. The sky was dominated by a lunar disk that looked impossibly large. That's evidence we can verify. Ancient coral fossils show growth rings that record daily and yearly cycles. Count the daily rings between annual markers, and you get days per year. Devonian corals from 400 million years ago show about 400 days per year. Same orbital period, shorter days. The math checks out perfectly. Earth's orbit around the Sun also isn't arbitrary. The 30 kilometers per second we travel is the exact speed required to maintain our distance from the Sun against its gravitational pull. Move slightly faster, and Earth would drift into a higher orbit, slightly slower, and we'd spiral inward. Over millions of years, planetary perturbations cause tiny variations, but they average out. The solar system is dynamically stable in ways that required billions of years to achieve. Jupiter's gravity shapes everything. Its massive influence cleared the asteroid belt, preventing those rocks from coalescing into another planet. It deflects comets that might otherwise bombard the inner solar system. Some scientists argue we wouldn't exist without Jupiter's protective presence, though that's debated. What's not debated is Jupiter's role in stabilizing Earth's orbit. Here's something strange, though. Venus rotates backward compared to most planets. Its day is longer than its year. Mercury rotates so slowly that one side stays scorching hot while the other freezes. These aren't random quirks. They're the results of specific events. Venus likely suffered a massive collision early in its history that flipped its rotation. Mercury's slow spin is tidally locked to the Sun in a 3-to-2 resonance, rotating exactly 3 times for every 2 orbits. The solar system's motion around the galaxy follows equally precise mechanics. That 230 km per second velocity isn't constant. It varies depending on our position in the galactic orbit. When we're on the side of the orbit moving with the galaxy's rotation, our speed relative to the galactic center increases. 6 months later, on the opposite side, it decreases. These variations are small but measurable. The Sun also bobs up and down through the galactic plane, crossing it roughly every 33 million years. Some researchers have proposed this vertical oscillation might correlate with mass extinction events on Earth. The idea is that passing through the dense galactic plane increases comet impacts or cosmic ray exposure. Evidence for this is weak, but it's a reminder that galactic dynamics might influence life on Earth in ways we're only beginning to explore. Now consider what's pulling us. The Great Attractor isn't a single object, but a massive concentration of galaxy clusters about 150 to 250 million light-years away. It's hidden behind the Milky Way's galactic plane, obscured by dust and stars, which is why it took so long to discover. Its gravitational pull affects hundreds of thousands of galaxies, drawing them toward it at hundreds of kilometers per second. But the Great Attractor itself is being pulled by something larger, the Shapley supercluster, an even more massive structure containing thousands of galaxies, and both are part of Laniakea, a supercluster spanning 500 million light-years. The name means immense heaven in Hawaiian, chosen because one of the astronomers who mapped it works in Hawaii. Laniakea contains about 100,000 large galaxies. Its total mass is roughly 100 quadrillion times the Sun's mass. All these galaxies are flowing together like streams merging into a river, following the contours of dark matter filaments that stretch across the universe. These flows define cosmic structure on the largest scales we can observe. What's outside Laniakea? We're not sure yet. The observable universe contains perhaps 2 trillion galaxies, organized into similar superclusters, all connected by dark matter filaments in a vast cosmic web. Between the filaments are voids, regions where galaxies are sparse. The universe looks like foam at the largest scales, with matter concentrated in sheets and filaments surrounding empty bubbles. This structure formed from tiny density fluctuations in the early universe, amplified by gravity over billions of years. The cosmic microwave background shows these fluctuations as temperature variations of 1 part in 100,000. Denser regions attracted more matter, growing into the galaxy clusters and superclusters we see today. Sparser regions became voids. Dark matter drove this process. Normal matter alone couldn't have formed galaxies fast enough. Dark matter started clumping earlier, creating gravitational wells that normal matter fell into. Without dark matter, the universe would look completely different. Perhaps no galaxies at all, just diffuse clouds of gas. We still don't know what dark matter is. The leading candidates are WIMPs, weakly interacting massive particles, but decades of searching have found nothing. Alternative theories propose axions, sterile neutrinos, or modifications to gravity itself. Whatever it is, dark matter outweighs normal matter by about 6 to 1. Most of the universe's mass is invisible. Dark energy is even stranger. Discovered in 1998 through observations of distant supernovae, it's causing the universe's expansion to accelerate. This was completely unexpected. Astronomers thought expansion should be slowing due to gravity. Instead, it's speeding up. Dark energy makes up about 68% of the universe's total energy density. Dark matter accounts for 27%. Normal matter, everything we can see, touch, or detect directly, is just 5%. We live in a universe where 95% of the content is mysterious. The acceleration has profound implications for cosmic motion. Galaxies beyond a certain distance are receding faster than light due to the expansion of space itself. This doesn't violate relativity because they're not moving through space. Space between us and them is expanding. Eventually, these galaxies will disappear beyond our cosmic horizon, forever unreachable. In the far future, if dark energy remains constant, every galaxy cluster will become isolated. The Milky Way and Andromeda will merge, as will other galaxies in our local group. But everything beyond our local cluster will fade from view. Future astronomers won't be able to discover the Big Bang or cosmic expansion because the evidence will have literally expanded beyond detection. Right now, though, we can still observe most of the universe. The cosmic horizon is expanding, revealing galaxies whose light has taken billions of years to reach us. We see them as they were in the distant past, some when the universe was only a few 100 million years old. These ancient galaxies are moving away from us faster than nearby ones. That's Hubble's law. Recession velocity increases with distance. A galaxy twice as far away is receding twice as fast. This relationship holds throughout the observable universe, evidence that space itself is expanding uniformly. Measuring these recession velocities requires analyzing redshift. How much a galaxy's light has been stretched toward longer wavelengths. The more redshifted, the faster the recession. The most distant galaxies have redshifts above 10, meaning their light has been stretched by factors of more than 10. They're receding at significant fractions of light speed, but that's recession due to expansion. Their peculiar velocities, motion through space relative to the expansion, add another layer. The galaxy's total velocity combines its peculiar velocity with the expansion velocity. Untangling these components requires careful analysis. For nearby galaxies, peculiar velocities dominate. Andromeda is moving toward us despite cosmic expansion because local gravity overwhelms expansion on these scales. The local group is gravitationally bound. Expansion doesn't affect it. Same for galaxy clusters. Expansion only dominates at scales larger than several 100 million light-years. This creates a hierarchy of motion. You rotate with Earth. Earth orbits the Sun. The solar system orbits the galaxy. The galaxy falls toward the Great Attractor. Laniakea flows through space, and underlying everything, space itself expands. Each motion operates on different timescales. Earth completes a rotation in 24 hours. An orbit around the Sun takes a year. The solar system's galactic orbit requires 230 million years. The Milky Way's fall toward the Great Attractor spans billions of years. Cosmic expansion is eternal, stretching on indefinitely. These motions also involve different forces. Earth's rotation is governed by angular momentum conservation. Its orbit follows solar gravity. The solar system's galactic orbit traces dark matter's gravitational pull. The Milky Way's motion toward the Great Attractor responds to massive concentrations of matter. Cosmic expansion is driven by dark energy, a force we barely understand. You're experiencing all of this simultaneously. Right now, as you sit still, you're participating in motions spanning 18 orders of magnitude in timescale, from Earth's rotation measured in hours to cosmic expansion measured in billions of years. And you feel none of it. That's the strangest part. All this tremendous velocity produces no sensation because you're in free fall through space-time. Einstein realized that free fall and floating in empty space are indistinguishable. Gravity isn't a force pulling you down. It's the curvature of space-time you're following. When you stand on Earth's surface, you're not in free fall. The ground pushes up, creating the sensation of weight. But in orbit, Astronauts are in continuous free fall around Earth, which is why they float. Earth is in free fall around the Sun. The Sun is in free fall around the galactic center. The galaxy is in free fall through the universe. Free fall feels like nothing. That's why you don't feel Earth's rotation, its orbit, or any of the larger motions. You're following spacetime's curvature along with everything around you. No relative motion means no sensation. This connects to something fundamental about reality. Motion is relative. There's no absolute frame of reference to measure against. When we say Earth rotates at 1,674 kilometers per hour, we mean relative to a frame where the distant stars appear fixed. When we say the solar system moves at 230 kilometers per second around the galaxy, we mean relative to the galactic center. But the galactic center itself is moving. Relative to what? The local group. And the local group is moving relative to the Virgo cluster. And the Virgo cluster relative to Laniakea. And Laniakea relative to the cosmic microwave background. The CMB provides the closest thing to an absolute reference frame because it represents the large-scale average motion of matter in the universe. But even that's still technically relative. It's just a very large averaging frame. Einstein's relativity says there's no privileged reference frame. All motion is relative. Yet we can still measure meaningful velocities by choosing appropriate reference frames for each scale of motion. This is why the November 2025 finding is so intriguing. If confirmed, it suggests our velocity relative to the galactic center is much higher than calculated from stellar dynamics. That discrepancy points to either more dark matter than models predict, a different distribution of dark matter, or possibly something wrong with our understanding of galactic dynamics. The implications ripple outward. If galaxy rotation curves need revision, so might cosmological models. Dark matter distribution affects structure formation throughout the universe. Get that wrong, and predictions about galaxy evolution, cluster formation, and cosmic expansion might need adjustment. Science builds knowledge layer by layer. Each measurement depends on previous ones. Revise one fundamental value, and you potentially revise everything built on it. That's why extraordinary claims require extraordinary evidence. One study isn't enough. Other teams need to verify the findings using independent methods. That process is happening now. Astronomers worldwide are examining the radio galaxy data, checking for systematic errors, looking for alternative explanations. Maybe the distribution pattern has another cause. Maybe there's a selection effect in which radio galaxies we detect. Maybe cosmic structure along our line of sight creates the observed asymmetry. Or maybe we really are moving 3 times faster than we thought. And that would reshape our understanding of the Milky Way's dynamics, dark matter's distribution, and galactic motion throughout the universe. Either way, the answer will teach us something. That's how progress works in science. Challenging a theory is easy. Confirming one is brutal. You don't just need telescopes and data. You need time, patience, independent verification from teams who have nothing to gain from agreeing with you. That's where the November 2025 study sits right now. 1 paper, significant findings, 0 confirmation. The team measured radio galaxy distribution across the sky. They found asymmetry. More galaxies appear in the direction the solar system travels through the galaxy. That creates what they call a headwind effect. Like walking through snow, more flakes hit your face than your back. From that asymmetry, they calculated velocity. 3 times higher than stellar dynamics predict, a 5 sigma result, meaning the probability this happened by chance is roughly 1 in 3.5 million. Those are strong odds. But extraordinary claims need extraordinary evidence. Other astronomers are already working on it. Some are reanalyzing the same radio galaxy data, checking for systematic errors the original team might have missed. Others are using completely different methods, stellar velocities, gas cloud motions, gravitational measurements, to see if they get similar results. This is science at its best. A claim gets made. The community tests it relentlessly. If it survives scrutiny, it becomes accepted. If it doesn't, we learn what went wrong and move forward smarter. But while verification unfolds, let's explore what this finding could mean if it holds up. Because the implications touch everything from dark matter to cosmic structure to how galaxies form and evolve. Start with dark matter itself. We know it exists. Galaxy rotation curves prove it. Gravitational lensing confirms it. The cosmic microwave background requires it. Without dark matter, the universe doesn't work. But we don't know what dark matter is. We've never detected a dark matter particle directly. We infer its presence through gravitational effects. That's it. So every measurement of dark matter's distribution, every clue about how it behaves, matters enormously. If the solar system really moves 3 times faster than we thought, that tells us something about the Milky Way's mass distribution. More specifically, it tells us about dark matter's distribution within our galaxy. Current models place most of the Milky Way's dark matter in a roughly spherical halo extending far beyond the visible disk. The dark matter density drops off with distance from the galactic center, following what's called an NFW profile, named after the physicists who first proposed it. These models predict stellar velocities based on the gravitational pull from both visible matter and dark matter. The predictions match observations pretty well. Not perfectly, but well enough that we trust the basic framework. A 3-fold velocity increase breaks that framework. It means either there's far more dark matter than models predict, or it's distributed differently than we assumed, or something else is wrong with our understanding of galactic dynamics. Each possibility opens new questions. More dark matter means revising mass estimates for the Milky Way. That affects calculations of the local group's total mass, which affects predictions about the Milky Way-Andromeda collision, which affects our understanding of how galaxy mergers work. Different dark matter distribution is even more interesting. Maybe dark matter doesn't follow an NFW profile. Maybe it clumps differently. Maybe there are dense streams or filaments we haven't detected. Maybe the smooth halo picture is wrong. Testing that requires simulations. Lots of them. Researchers would run thousands of models with different dark matter distributions, see which ones produce the observed velocity, then check if those models match other observations of our galaxy. That's a multi-year project, maybe decade-long, which is why one study isn't enough. We need convergent evidence from multiple independent sources before rewriting galactic models. But there's another possibility worth considering. What if the velocity measurement is right, but it's not telling us about dark matter at all? What if it's revealing something about how we measure velocities in the first place? Think about the challenge. We're sitting on a planet orbiting a star that's orbiting a galaxy. We're trying to measure how fast that galaxy orbit happens. But we can't step outside the system. We have to measure from within, so we observe other stars. We measure their positions and velocities relative to us. We build statistical models of how stars move through the galaxy. From those models, we calculate the Sun's orbit around the galactic center. That method works if our sample of stars is representative. If it's biased somehow, maybe we're observing certain types of stars more than others, or stars in certain regions more than others, our velocity estimate could be off. The radio galaxy method bypasses that problem. It doesn't rely on stellar motions within the Milky Way. It uses extragalactic sources, distant radio galaxies that are effectively fixed points in the cosmic reference frame. The asymmetry in radio galaxy distribution comes from the Doppler effect. As we move through space, we see slightly more galaxies ahead than behind. It's a direct measurement of our motion relative to the universe at large. If this method gives a different answer than stellar dynamics, one of them is wrong, or both are partly wrong, or they're measuring different things that we haven't properly distinguished. That last option is intriguing. Maybe the solar system's motion through the galaxy has components we haven't fully accounted for. Maybe there are local perturbations, nearby star clusters, molecular clouds, spiral arm dynamics that affect our trajectory in ways the smooth galactic potential models don't capture. The galaxy isn't a perfect symmetric system. It has structure, spiral arms where star density is higher, the galactic bar, that elongated bulge at the center, satellite galaxies being torn apart by tidal forces. All of this creates gravitational irregularities. Our solar system's path through this lumpy potential would be more complex than simple circular motion around the galactic center. We might be oscillating vertically through the galactic plane. We might be moving radially inward or outward. We might be affected by resonances with the spiral arm pattern. Disentangling all these components requires sophisticated modeling. And maybe the stellar dynamics method captures some components better, while the radio galaxy method captures others. Reconciling them could reveal new physics about how stars actually move through galaxies. Here's something else to consider. The measurement depends on knowing our position in the galaxy. We're roughly 26,000 light-years from the galactic center, but roughly matters. Uncertainty in that distance translates to uncertainty in velocity calculations. Recent measurements using parallax, the apparent shift in star positions as Earth orbits the Sun, have refined our distance to the galactic center. But there's still uncertainty. A 10% error in distance means a 10% error in orbital velocity. Could that explain the discrepancy? Probably not entirely. A threefold difference is too large, but it might account for part of it. Combined with dark matter distribution uncertainties and stellar dynamics complexities, you could potentially close the gap. That's the unglamorous reality of precision astronomy. Every measurement has error bars. Every model has assumptions. Reconciling different methods means carefully tracking all those uncertainties and assumptions, seeing where they agree and where they don't. It's slow work, tedious work, the kind that doesn't make headlines, but it's how we actually figure things out. Now zoom out. Assume the velocity finding holds up. What does that mean for cosmology more broadly? It means our understanding of galactic dynamics needs revision. That's significant because galaxy formation and evolution are central to cosmology. The lambda cold dark matter model, our standard cosmological framework, makes specific predictions about how galaxies form from dark matter halos, how they grow through mergers, how they distribute throughout the universe. If we're wrong about the Milky Way's dynamics, we might be wrong about other galaxies too. That could affect estimates of dark matter density throughout the universe. It could change predictions about structure formation. It could alter calculations of the universe's expansion rate. Those are big dominoes. Tip 1. Others might follow. But cosmology has survived upheavals before. The discovery of dark energy in the late 1990s completely changed our understanding of cosmic expansion. It forced revision of nearly every cosmological model. Yet the field adapted. New models emerged. Better observations refined them. Science progresses through exactly this kind of challenge and revision cycle. A surprising result appears. It either gets confirmed or refuted. Either way, we learn something. If confirmed, we revise our models. If refuted, we understand our measurement methods better. The November 2025 study is at the beginning of that cycle. The claim is made. Now comes verification. Other teams will attempt to replicate the findings. They'll use different data sets, different analysis methods, different assumptions. If multiple independent teams reach similar conclusions, confidence builds. If they don't, we look for where the original analysis went wrong. Both outcomes advance knowledge. Meanwhile, theoretical physicists are already exploring implications. What if the velocity really is 3 times higher? What would that require in terms of dark matter distribution? What observable predictions would that make? Can we test those predictions? That's how theory and observation work together. Observation finds something unexpected. Theory tries to explain it. Those explanations make new predictions. Observation tests them. The cycle continues. This particular cycle might take years, maybe a decade. Precision measurements of galactic dynamics aren't quick, but the investment pays off in understanding not just our galaxy, but how all galaxies work. Because the Milky Way is special to us, it's our home. But it's not special cosmically. It's a fairly typical spiral galaxy. Understanding its dynamics helps us understand billions of other galaxies throughout the universe. Every galaxy is orbiting something. Every galaxy cluster is moving through space. Every supercluster is flowing toward gravitational attractors. The entire cosmic web is in motion, driven by dark matter's gravitational pull and dark energy's repulsive push. Measuring those motions accurately lets us map dark matter's distribution across cosmic scales. That tests cosmological models. It constrains dark energy's properties. It reveals how structure formed and evolved over billions of years. So a measurement of the solar system's velocity, seemingly local, seemingly specific to our situation, actually connects to questions about the universe's entire structure and history. That's the beauty of cosmic motion. Everything is connected. Change one measurement and effects ripple outward through every scale, from stellar dynamics to galactic evolution to cosmological models. The question now is whether this particular measurement will create those ripples. Is it real? Is it revealing something profound? Or is it an artifact that will fade under scrutiny? Only time and careful science will tell. The data exists, the tools exist, the expertise exists. What's needed now is the patient, methodical work of verification and validation. That work takes time. Lots of time. Radio telescope observations require months of data collection. Statistical analyses demand careful scrutiny from multiple independent researchers. Peer review moves at its own deliberate pace. There's no rushing the scientific method when claims this extraordinary are at stake. While that verification unfolds, we can appreciate what the controversy reveals about astronomy itself. A century ago, we barely knew other galaxies existed. We thought the Milky Way was the entire universe. Now we're arguing about whether our solar system's orbital velocity is 230 or 700 kilometers per second. That's not just progress, it's astonishing progress. The tools enabling these debates didn't exist a generation ago. Radio galaxy surveys mapping millions of objects across the sky. Precision measurements of stellar velocities down to meters per second. Computer models simulating galactic dynamics over billions of years. All these capabilities developed within living memory. Consider what's actually being measured here. Radio galaxies emit radiation from jets powered by supermassive black holes at their centers. Those jets can extend hundreds of thousands of light years into space. The radiation travels across the universe for billions of years before reaching our telescopes. We detect it, analyze its properties, map its distribution across the sky, and use that distribution to infer our motion through space. Every step in that chain requires precision instruments and sophisticated analysis. Radio telescopes must distinguish signals from cosmic sources against the noise from Earth's atmosphere and human technology. Computer algorithms must identify which radio sources are galaxies versus stars or other objects. Statistical methods must extract meaningful patterns from datasets containing millions of measurements. The fact that we can do this at all is remarkable. That we can do it well enough to detect discrepancies between measurement methods is even more impressive. Whether the November 2025 result stands or falls, the capability to make such measurements represents genuine scientific achievement. Meanwhile, our cosmic motion continues unchanged. Earth spins at over 1,000 miles per hour at the equator, completing one rotation every 24 hours. You're moving that fast right now, yet you feel nothing because everything around you moves together. The atmosphere, oceans, buildings, ground, all rotating in perfect synchronization. Earth simultaneously orbits the Sun at nearly 70,000 miles per hour. That's fast enough to circle the planet's diameter in 7 minutes. Again, no sensation. The motion is too smooth, too constant. Only acceleration produces feeling, and Earth's orbital path changes direction so gradually that the acceleration is imperceptible. The Sun carries Earth and the other planets around the Milky Way's center at, well, that's the disputed number. Somewhere between 500,000 and 1.6 million miles per hour, depending on which measurement you trust. Even at the lower estimate, that's incomprehensibly fast by human standards. At the higher estimate, it's ludicrous. The Milky Way itself moves relative to nearby galaxies. It's approaching Andromeda at about 250,000 miles per hour. In 4 billion years, they'll collide. Not a violent crash. Galaxies are mostly empty space, but a gravitational dance that will reshape both over hundreds of millions of years. Stars will be flung into new orbits. Gas clouds will collide and ignite new star formation. The two supermassive black holes will eventually merge. Our Sun will probably survive that merger. Most stars will. They'll just end up in different locations within the combined galaxy. Some simulations suggest our solar system might be ejected entirely, flung into intergalactic space. Others show it settling into the merged galaxy's outer halo. Either way, it's not something to worry about. 4 billion years is a long time. The Sun will have already begun expanding into a red giant by then, making Earth uninhabitable long before the galactic merger matters. Beyond local galaxy interactions, the Milky Way participates in larger scale flows. The local group of galaxies moves toward the Virgo cluster. That motion, combined with flows toward the Great Attractor and the Shapley supercluster, produces our motion relative to the cosmic microwave background, about 552 kilometers per second in a specific direction through space. These nested layers of motion create a dizzying picture. You're on a spinning planet orbiting a star that's orbiting a galactic center, while the galaxy itself moves through space toward other galaxies and larger structures, all while the universe expands around everything. Yet despite these absurd velocities, there's a sense in which you're not moving at all. Relative to your chair, you're stationary. Relative to the ground beneath you, motionless. That's Einstein's insight about relativity. Motion is meaningless without specifying what you're moving relative to. There's no absolute reference frame, no cosmic measuring stick against which to judge true velocity. The cosmic microwave background comes closest to providing an absolute reference. It represents the universe's average rest frame, the reference frame in which the CMB appears uniform in all directions. Our motion relative to the CMB is about as close to absolute velocity as physics allows. But even that's relative in a sense. The CMB frame isn't privileged by physics. It's just useful for cosmology. An observer in another galaxy would measure their own velocity relative to the CMB and get a different number. Neither measurement is more correct than the other. This philosophical point matters for interpreting the November 2025 study. When researchers claim the solar system is moving faster than expected, they mean relative to specific reference frames defined by radio galaxy distributions. Change the reference frame and the velocity changes too. What matters isn't the absolute number, but whether it's consistent with our models of galactic dynamics. If multiple independent measurement methods yield inconsistent velocities, something's wrong somewhere. Either the measurements have systematic errors, or the models are incomplete, or both. Resolving that inconsistency advances understanding, regardless of which specific velocity value is ultimately correct. That's worth remembering amid the excitement over potentially revolutionary findings. Scientific progress doesn't always come from confirming dramatic new claims. Sometimes it comes from carefully explaining why a dramatic claim was wrong. Both outcomes teach us something. The Michelson-Morley experiment in 1887 found no evidence for the luminiferous ether that physics predicted should fill all space. That null result, finding nothing where something was expected, revolutionized physics. It helped inspire Einstein's special relativity, which eliminated the ether entirely and reconceptualized space and time. Similarly, careful measurements that ultimately reject the November 2025 velocity claim would still advance knowledge. They'd teach us about systematic errors in radio galaxy surveys, about subtleties in statistical analysis, about unexpected complications in modeling galactic dynamics. All valuable lessons. Or maybe the claim holds up. Maybe after extensive verification, multiple independent teams confirm that yes, the solar system really is moving 3 times faster than previous estimates suggested. Then we get the revolution. Cosmological models need revision. Dark matter distribution requires rethinking. Our understanding of galactic dynamics gets a major update. Either way, we learn. That's science functioning as designed. Make observations, propose explanations, test predictions, refine understanding, repeat indefinitely. The current moment represents just one iteration in that endless cycle. One team made a surprising measurement using radio galaxies. Other teams will attempt to verify it using different methods. The results will either converge or diverge. If convergence, confidence builds. If divergence, we investigate the discrepancy. Years from now, we'll look back on the November 2025 announcement as either the beginning of a major shift in cosmology or an interesting false alarm that taught us valuable lessons about measurement systematics. Both outcomes are scientifically productive. What makes this particular controversy compelling is its connection to fundamental questions. How does dark matter behave? How did galaxies form and evolve? What forces shape cosmic structure at the larger scales? These aren't abstract academic puzzles. They're questions about reality's basic architecture. The distribution of dark matter throughout the universe determines how galaxies move. Measure those motions precisely, and you map dark matter's distribution. That tests theories about what dark matter actually is. Particles, modified gravity, something else entirely. The data constrains possibilities. Similarly, understanding galactic velocities helps explain how structure formed after the Big Bang. The early universe was nearly uniform, tiny density fluctuations of 1 part in 100,000. Over billions of years, gravity amplified those fluctuations into the cosmic web of galaxies, clusters, and voids we observe today. But gravity alone isn't enough. The timeline doesn't work with only ordinary matter. Dark matter's extra gravitational pull is necessary to explain how structure formed as quickly as it did. Measure how fast galaxies move, and you test whether dark matter models correctly predict that motion. So arguments about the solar system's orbital velocity aren't really about one number. They're about whether our entire cosmological framework is accurate. That's why astronomers care so much about getting the measurement right. The stakes extend beyond cosmology. If we're wrong about galactic dynamics, we might be wrong about dark energy too. Dark energy drives the universe's accelerating expansion, counteracting gravity's attractive pull. Measuring that acceleration requires understanding how galaxies move and how their motion changes over time. If systematic errors affect velocity measurements, those errors could propagate into dark energy estimates. That would affect predictions about the universe's ultimate fate. Will expansion continue accelerating forever? Will it eventually slow? The answer depends partly on accurately measuring cosmic velocities at various scales. This interconnectedness is both beautiful and frustrating. Beautiful because it reveals deep unity in cosmological understanding. Everything connects to everything else. Frustrating because errors anywhere in the measurement chain affect conclusions everywhere else. The November 2025 study might be highlighting exactly such an error, or it might be revealing a genuine gap in our models. Only continued investigation will determine which. The important thing is that the investigation happens. The question gets asked. The measurements get scrutinized. The models get tested. That process is science at its best. Not accepting claims uncritically, not rejecting them reflexively either, but engaging seriously with new evidence, attempting replication, investigating discrepancies, following the data wherever it leads. Right now, you're moving through space at somewhere between 500,000 and 1.6 million miles per hour, depending on whose measurements you trust. That uncertainty matters for understanding how the Milky Way works, how dark matter behaves, and how the universe evolved. Over the coming years, better observations and more careful analysis will narrow that uncertainty. We'll converge on an answer, and that answer, whatever it turns out to be, will teach us something profound about our place in the cosmos and the forces that shape it. Somewhere above you right now, photons are streaming past Earth at 186,000 miles per second. They've been traveling for years, decades, maybe centuries from distant stars. And here's what's strange. From their perspective, no time has passed at all. They left their star and arrived at your eye in the same instant. Time doesn't exist for light, but for you, time moves forward relentlessly, 1 second per second. 24 hours per day, you're aging at a specific rate determined by your velocity through space and your position in Earth's gravitational field. Move faster, and you'd age slower. Climb higher, and your clock would tick faster. These aren't hypothetical effects. They're measured realities that GPS satellites must account for every microsecond. Your motion through space isn't just about distance traveled. It's about the fundamental structure of space-time itself. Every velocity we've discussed, Earth's rotation, its orbit, the Sun's galactic journey, the Milky Way's cosmic voyage, represents a different way of slicing through the four-dimensional fabric of reality. When you stand still on Earth's surface, you're not actually stationary in space-time. You're moving through time at maximum speed. Start moving through space, and your motion through time slows down. It's a trade-off. The faster you go through space, the slower you go through time. Light moves through space at maximum speed, so it doesn't move through time at all. This connects everything we've explored. The reason you don't feel Earth's rotation isn't just that everything around you rotates together. It's that you're all following the same path through space-time. You're in freefall through curved geometry, and freefall feels like nothing. Einstein figured this out by thinking about elevators. Imagine you're in an elevator in deep space, far from any gravity. Someone outside starts pulling the elevator upward at a constant acceleration. Inside, you'd feel weight. Your feet would press against the floor. You couldn't tell whether you were accelerating through space or standing still in a gravitational field. Now flip it. You're in an elevator on Earth. The cable snaps. As you fall, you'd feel weightless. Everything in the elevator would float. You couldn't distinguish freefall in Earth's gravity from floating in empty space far from any mass. That's the equivalence principle. Acceleration and gravity are the same thing, which means gravity isn't really a force pulling you down. It's the curvature of space-time causing you to accelerate even when you think you're standing still. Right now, the ground is pushing up on your feet. That's what you feel as weight. But if the ground vanished, you'd start falling. Not because some force grabbed you, but because you'd finally be free to follow space-time's natural curvature. Freefall is the natural state. Standing still requires constant acceleration upward. This is why astronauts orbit Earth at 17,500 miles per hour, yet feel weightless. They're in freefall. The station is falling toward Earth. They're falling toward Earth, and everything inside is falling together at the same rate. No relative motion means no sensation. It's the same principle at every scale. Earth is in freefall around the Sun. The Sun is in freefall around the galactic center. The galaxy is in freefall through the universe's gravitational landscape. All these tremendous velocities produce no sensation because they're all freefall through curved spacetime. The November 2025 study suggesting we're moving 3 times faster than expected. If confirmed, it means spacetime's curvature in our region of the galaxy is different than models predict. More dark matter creating stronger curvature, or different dark matter distribution creating different curvature patterns. Either way, it's about geometry, not just speed. This is what makes cosmology so fascinating. We're not just measuring how fast things move, we're mapping the shape of space-time itself. Every velocity measurement is really a measurement of curvature. Every trajectory traces a geodesic through 4-dimensional geometry. The cosmic microwave background, that ancient light from 380,000 years after the Big Bang, shows us space-time's curvature on the largest scales. Tiny temperature fluctuations represent tiny variations in density, which represent tiny variations in curvature, which grew over billions of years into the massive structures we see today. You're inside one of those structures right now. The Milky Way formed from an overdense region in the early universe. Gravity pulled matter inward, creating stronger curvature, pulling in more matter, creating stronger curvature in a feedback loop that built galaxies. Dark matter amplified this process. Its extra gravity created deeper gravitational wells, pulling normal matter into the patterns that became stars and planets. Without dark matter, the universe would be far more uniform. Maybe no galaxies at all, certainly no solar systems, definitely no people wondering about cosmic motion. So when we measure the solar system's velocity around the galaxy, we're really measuring the curvature of spacetime created by dark matter's gravitational influence. Get that measurement right, and we constrain dark matter's properties. Get it wrong, and our entire picture of how galaxies work might need revision. That's why the November 2025 study matters. Not because a specific velocity number is intrinsically important, but because it might be revealing something fundamental about reality's structure. Here's what we know for certain. You're moving. Fast. Absurdly fast by any reasonable standard. Earth spins at over 1,000 miles per hour. Orbits the Sun at 67,000 miles per hour. Circles the galaxy at somewhere between 500,000 and 1.6 million miles per hour. The exact number still disputed. The galaxy itself moves through space at over 1 million miles per hour relative to the cosmic microwave background. Stack all those motions together, and you're traveling through space at velocities that make supersonic jets look stationary. Yet you feel nothing. Your coffee sits calmly in its cup. Papers rest undisturbed on your desk. The air in the room doesn't howl past at 1 million miles per hour. This perfect calm in the midst of cosmic chaos reveals something profound about the nature of motion itself. There's no absolute motion, only relative motion. There's no absolute rest, only rest relative to chosen reference frames. The universe doesn't have a preferred frame of reference, some cosmic benchmark against which to measure true velocity. Einstein called this the principle of relativity, and it's more than just physics, it's almost philosophical. The idea that motion is meaningless without specifying what you're moving relative to, that all reference frames are equally valid. that the laws of physics work the same whether you're standing still on Earth or flying through space at 1,000,000 miles per hour. This is why we can have debates about whether the solar system is moving at 230 or 700 kilometers per second. Both numbers might be correct depending on reference frame and measurement method. What matters is consistency. Do different measurement methods agree when properly accounting for their reference frames? If they don't agree, something's wrong. Either systematic errors in measurements, or gaps in theoretical models, or both. Resolving the discrepancy teaches us something either way. Meanwhile, the cosmic motions continue regardless of our measurements. Earth keeps spinning. The sun keeps orbiting. Galaxies keep flowing through space, following gravitational gradients shaped by dark matter. The universe keeps expanding, carrying distant galaxies away from us faster than light. None of these motions need our understanding to proceed. They happened for billions of years before humans existed. They'll continue billions of years after we're gone. The universe doesn't care whether we accurately measure its motion, but we care. We're curious creatures who emerged from cosmic matter and developed the capacity to wonder about our origins and context. We build telescopes to observe distant galaxies. We launch satellites to measure cosmic microwave background radiation. We develop theories to explain what we see and make predictions we can test. This drive to understand isn't separate from the cosmic story. It's part of it. The universe became complex enough to generate life. Life became complex enough to generate consciousness. Consciousness became sophisticated enough to study the universe that created it. You're the universe examining itself, made of particles forged in stellar cores billions of years ago, arranged in patterns complex enough to contemplate their own cosmic motion, asking questions about velocity and reference frames and the nature of space-time. That capacity for wonder, that ability to look up at the night sky and ask how fast we're really moving, represents something remarkable in cosmic history. For most of the universe's existence, motion happened without anything being aware of it. Galaxies formed, stars ignited, planets coalesced, all without consciousness observing or measuring. Then, on at least one planet, maybe others, matter organized itself into forms capable of observation and measurement, capable of building instruments to detect radio galaxies billions of light years away, capable of analyzing their distribution to infer our motion through space. The fact that we can make such measurements, that we can detect discrepancies between methods, that we can debate the implications, all of this represents consciousness examining the substrate from which it emerged. Whether the solar system moves at 230 or 700 kilometers per second around the galaxy, you're still here, still moving, still part of the cosmic dance. The exact velocity number matters for models and theories, but the deeper truth is simpler. Motion is fundamental to existence itself. Nothing in the universe stands still. Even atoms are constantly vibrating. Electrons orbit nuclei. Molecules collide and bond. Cells divide and grow. Planets rotate and orbit. Stars circle galaxies. Galaxies flow through space. The universe expands. Motion is what separates existence from void. A universe without motion would be dead, static, frozen. Motion brings change, and change brings possibility. The possibility that simple atoms could become complex molecules, that molecules could become cells, that cells could become organisms capable of measuring their own cosmic velocity. You're part of that grand progression from simplicity to complexity, from hydrogen clouds to conscious beings wondering about their place in the cosmos. And your place is here, now, moving through space at ridiculous speeds that feel like perfect stillness. That paradox, tremendous motion that produces no sensation, captures something essential about reality. The universe is far stranger than everyday experience suggests. Space-time curves, time dilates, particles exist in superposition, galaxies recede faster than light, dark matter outweighs normal matter 6-1. Yet despite all this strangeness, the universe is comprehensible. We can measure it, model it, make predictions that match observations. The November 2025 study proposing faster velocities, that's science working exactly as intended. Make observations, propose explanations, test predictions, revise models, repeat endlessly. This process has carried us from thinking Earth was the center of everything to understanding we're on a planet orbiting a typical star in a typical galaxy, in a typical region of space. From believing the Milky Way was the entire universe to knowing it's one of perhaps 2 trillion galaxies in the observable universe alone. Every step required letting go of assumptions, accepting that reality doesn't conform to intuition, following evidence wherever it leads, even when it leads somewhere uncomfortable or strange. The suggestion that we're moving 3 times faster than expected is uncomfortable. It challenges established models. It requires explaining where previous measurements went wrong or where models are incomplete. That's difficult work, but difficulty doesn't make it wrong. Maybe we really are moving faster. Maybe dark matter is distributed differently than models predict. Maybe there are components to galactic dynamics we haven't properly accounted for. If so, revising our understanding will ultimately give us a more accurate picture of how the universe actually works. Or maybe the new measurement has systematic errors that careful analysis will reveal. Maybe reconciling different measurement methods will teach us something subtle about observational biases or statistical analysis. That outcome is valuable too. Either way, asking the question matters. Taking the measurement seriously matters. Doing the hard work of verification matters. That's how knowledge advances. And while that process unfolds, you keep moving, spinning with Earth, orbiting with the Sun, circling with the galaxy, flowing with the local group, participating in cosmic motions spanning 18 orders of magnitude in scale, from hours to billions of years. You're simultaneously spinning at 1,000 miles per hour and moving at over 1,000,000 miles per hour, yet experiencing perfect stillness. You're simultaneously ancient, made of atoms billions of years old, and ephemeral, a temporary pattern in matter's constant rearrangement. You're simultaneously insignificant, one person among billions on one planet among trillions, and central, the only perspective from which you can observe the universe, making your viewpoint uniquely valuable. These paradoxes aren't problems to solve. They're features of existence in a universe strange enough to generate consciousness from stellar debris. The motion never stops. Earth keeps spinning at 1,674 kilometers per hour at the equator, keeps orbiting the Sun at 107,000 kilometers per hour. The Sun keeps circling the galaxy at whatever velocity better measurements will eventually confirm. The galaxy keeps flowing through space at hundreds of kilometers per second. All of this motion traces paths through space-time, determined by matter's distribution and the curvature it creates. Dark matter's gravitational influence shapes those paths on galactic scales. dark energy shapes them on cosmic scales. The interplay between gravity pulling inward and expansion pushing outward creates the universe's large-scale structure. You're embedded in that structure, made of matter governed by the same forces shaping galaxies and superclusters, subject to the same laws of motion and gravitation, part of the same cosmic web stretching across billions of light years. Understanding your motion through that web, whether you're moving at 230 or 700 kilometers per second around the galaxy, connects you to questions about dark matter, galactic dynamics, cosmic structure, and the ultimate fate of the universe itself. Those questions don't have final answers yet. Maybe they never will. The universe might be too complex, too vast, too strange for complete understanding. But the pursuit of understanding is worthwhile, regardless of whether we reach the destination. Because in pursuing these questions, we're doing something remarkable. We're using minds evolved to find food and avoid predators to contemplate the structure of space-time. We're using instruments built from stellar debris to observe radiation from the Big Bang's afterglow. We're using mathematics developed to solve practical problems to model dark matter halos and cosmic expansion. We're taking the raw materials the universe provided, atoms, energy, physical laws, and fashioning them into tools for understanding the universe itself. That recursive loop of the universe studying itself through conscious agents it generated is perhaps the strangest phenomenon of all. The velocities are impressive. 1,000 miles per hour, 67,000 miles per hour, maybe 1,000,000 miles per hour. These numbers capture attention with their magnitude. But the deeper marvel is that you can know these numbers, that you can measure cosmic motion from inside the system, that you can build telescopes and satellites and mathematical models that reveal truths about reality, invisible to naked perception. That capacity to know, to measure, to calculate, to understand, represents something extraordinary in cosmic history. For billions of years, the universe evolved without anything being aware of its own evolution. Matter clumped into stars without consciousness observing. Galaxies formed without anyone measuring their velocities. Then complexity reached a threshold. Consciousness emerged, and for the first time, the universe could contemplate itself. You're part of that contemplation right now, reading about cosmic velocities, wondering about dark matter, considering whether new measurements might revise established models, participating in humanity's ongoing attempt to understand its context. That participation matters. Not because any individual contribution is likely to revolutionize cosmology, though it might, but because the collective effort of curious minds gradually illuminates reality's structure. Each measurement refines understanding. Each theory explains more phenomena. Each generation builds on previous knowledge, seeing farther because they stand on the shoulders of those who came before. The November 2025 Radio Galaxy study is one small step in that endless journey. Whether it ultimately confirms faster velocities or reveals measurement errors, it advances the conversation. It gives us new data to analyze, new questions to investigate, new mysteries to explore. And exploration is what we do. It's who we are. Curious primates on a spinning rock, using ingenuity and persistence to figure out how the cosmos works. Building instruments to extend our senses, developing mathematics to extend our reasoning, constructing theories to organize our observations into coherent frameworks. None of this was inevitable. The universe didn't have to generate consciousness. Stars could have burned through their fuel without ever creating the heavy elements needed for complex chemistry. Planets could have remained barren. Life could have stayed simple. But through whatever combination of physical law and random chance, complexity emerged. Simple atoms became molecules. Molecules became cells. Cells became organisms. Organisms became conscious. Consciousness became curious. And now you're here, moving through space at absurd velocities you can calculate but can't feel, made of atoms forged in stellar cores, contemplating your place in a universe vast beyond comprehension. The motion continues, always has, always will. Earth will keep spinning until tidal forces lock it to the sun billions of years from now. The sun will keep orbiting until the Milky Way merges with Andromeda. The merged galaxy will keep moving through space as the universe expands ever faster. Eventually, in the far future, expansion will carry every galaxy beyond every other galaxy's cosmic horizon. Each galaxy will become isolated, alone in its own observable universe. Stars will burn out. Black holes will evaporate. Even matter itself might decay. But that's trillions of years away. Right now, the universe is rich with structure and motion. Galaxies cluster together. Stars illuminate the darkness. Planets orbit. And on at least one of those planets, consciousness has emerged to wonder about it all. That's where you are. Moving at over 1 million miles per hour through a universe 13.8 billion years old, made of particles that have existed since shortly after the Big Bang, arranged in patterns complex enough to contemplate their own cosmic journey. The exact velocity number, whether 230 or 700 kilometers per second around the galaxy, will be resolved through careful science, multiple measurements, independent verification, rigorous analysis. The process takes time, but it works. Meanwhile, the deeper truth remains. You're moving. You're part of something vast and ancient and ongoing, and you have the extraordinary privilege of being aware of it. That awareness doesn't change the motion, doesn't affect the velocities, doesn't alter space-time's curvature or dark matter's distribution, but it means something. It means the universe has become complex enough to study itself. That consciousness has emerged capable of measuring cosmic motion. That matter has organized into forms that can contemplate their own origins. You're that contemplation made physical, stardust that learned to wonder, atoms that became aware, the universe's way of knowing itself. And right now, this moment, you're moving through space at speeds that would make light jealous if light experienced time. But you don't feel it. You sit in perfect stillness, reading about motion, participating in the universe's ongoing attempt to understand its own nature. That's the real marvel. Not the velocities themselves, impressive as they are, but the fact that velocity can be measured, understood, debated, refined. That conscious beings can emerge from cosmic matter and figure out how fast they're moving through space. The November 2025 study might revolutionize cosmology, or it might become a footnote about measurement errors. Either way, the fact that we can make such measurements, can debate their implications, can refine our understanding through careful analysis, that's the achievement worth celebrating. Because ultimately, the motion is just motion. Inevitable consequences of gravity and inertia and space-time curvature. What makes it meaningful is that you can know about it, can measure it, can wonder what it means. You're moving at over 1 million miles per hour right now, and you're sitting perfectly still. Both statements are true, depending on reference frame. That paradox captures something essential about reality's nature. Motion is relative, time is flexible, space curves. The universe is stranger than intuition suggests, but comprehensible to patient investigation. You're part of that investigation, not just as an observer, but as a participant, made of the same matter being studied, subject to the same forces being measured, following the same curved geodesics through space-time that galaxies follow. The cosmic dance continues. You're dancing along whether you feel it or not, moving through space at ridiculous speeds that produce no sensation, tracing paths through space-time determined by matter's distribution and gravity's influence. And somehow, impossibly, you're aware of it, conscious of your motion through an expanding universe, capable of measuring velocities and questioning measurements and refining understanding. That awareness is the universe contemplating itself, matter examining its own behavior, reality studying its own structure. You're not watching the cosmic dance from outside. You're part of the dance itself, moving, measuring, wondering, understanding, participating in the universe's ongoing evolution from simplicity to complexity, to consciousness, to comprehension. The motion never stops, but neither does the wonder.